going to talk about clustering with k-means, and clustering in our case refers to a very broad set of techniques that we use for finding subgroups or clusters in our dataset. We will try to look for a partition of the data into different groups so that the observations within each group are quite similar to each other. K-means is a very popular method for this, and this is the reason why we're using it to illustrate how to visualize the results of that particular method. In creating these different clusters, we basically want to satisfy two properties. The first one is that each observation belongs to at least one of the clusters, at least one of the groups. And the second one is that those clusters are non-overlapping. That means that no observation belongs to more than one cluster. The k-means algorithm can be summarized in these two steps. The first step is to randomly assign a number from 1 to k to each of your observations. And the second step is an iterative procedure. We iterate until the cluster assignment stops changing based on two properties. For each of the groups, we will compute the cluster centroid, and the kth cluster centroid is the vectors of p-feature means for the observations in that cluster. After that, we reassign each observation to the cluster whose centroid is closest to, where closest in this case is defined using the Euclidean distance. This beautiful animation using the artwork of Alison Horst and the folks at our studio illustrates how k-means clustering works. In this example, we're going to use the MPG dataset again, and we're going to focus on two variables, TISPL and highway, as we did before for the regression problem, using the k-means built-in function in ART, which has an implementation of this unsupervised learning technique. To show you how it works, again, we'll use the MPG mini data frame and simply use the k-means functions, which requires that you pre-specify the number of clusters under the parameter centers. After that, we can obtain the clustering assignments by taking a look at the cluster attribute of that clustering object. And therefore, we can create a visualization, a scatter plot like the one on the right-hand side here, where the cluster assignment is mapped to the color aesthetic. So you can see the three different groups that are assigned to different cars, in this case, in our example data set. A natural thing to do is ask yourself what would happen if you would change, increase, or decrease the value of k that represents the number of clusters that you want to create. So first, cluster the data 9 times, each using a different value of k, and then create columns containing the tidy, glance, and augmented data. So we are using now 3 functions from the broom package, and those are tidy, glance, and augment, that would allow us to keep track of all the different outputs provided by the k-means function when running a clustering method. In this case, we're also using the map function from the purrr package, and if you click on the link, you can see more about this documentation. What we have just created is something that we can then use to turn that information into 3 separate data sets, each representing a different type of data, using tidy, augment, and glance from the broom package. Now we can tidy up our data, tidy up our model, and do some data visualization for our results. We are using 3 different objects, cluster, assignments, and clusterings, and then using ggplot and the functions that we know already, in this case a scatter plot, and we're also using the facet wrap function, and then using the geonPoint function to plot 2 things: the different cars represented by a point in the space created by highway and displacement, and then their color based on their clustering assignment. In addition to that, we're also adding to the plot the position of the centroid for the different cluster, and now we're showing the reader how clustering would look if you consider any type of value of k from 1 to 9 in this case for this particular data set. The data that we obtain using the glance function actually fills a different but very important purpose because it allows us to view trends of some summary statistics across different values of k, in which our case was from 1 through 9. Of particular interest is something known as the total within sum of squares when we are trying to evaluate the results of a clustering algorithm. That is saved into the tot.width in SS column, and then if we have that, we can simply create a plot like the one shown on the right. This is called an elbow plot, and we look at these plots when evaluating the performance of our clustering methods and checking when the total within sum of square is not changing a lot while we vary the value of k. Another approach for clustering is what we know as hierarchical clustering, and this is an alternative to the k-means method that we discussed before. We describe a bottom-up or agglomerative clustering approach. This is one of the most common type of hierarchical clusterings and refers to the fact that a dendrogram is built starting from the leaves and combining clusters up to the trunk of a tree. Once again, we have a great animation using the artwork of Alison Horst that explains how hierarchical clustering works using a single linkage function. Remember that when working with hierarchical clustering, we get to choose the type of linkage function that we can use. Some of the most popular ones include complete, single, average, and centroid type of linkage. In terms of visualizing these results, we can also use a built-in function in R called hclust. This requires a computation of a distance matrix and is very easy to do. After that, we can use ggplot2 to create a scatter plot and color every single point based on their clustering assignments. Another option is to use the hcut function from the factoextra package, and in addition to that, use a function called @vis_dent for dendrogram. This is a very easy and super powerful way to create quick visualizations of your dendrogram to represent the clustering results. Again, just like we did for the k-means example, we can also make use of the map function from the purrr package to test multiple things. In this first example, we're testing what would happen if we were trying to create or observe how the dendrogram would look like when we try to group 2, 3, or 4 different clusters. The code for this, or the trick for this, is to create 3 different plots, again using the @vis_d function from the factoextra package, and after that we can just put them all together using a very cool package called patchwork that allows you to put together multiple objects, multiple plotting or multiple figures that you have created before. Evidently, you can also use the map function to test multiple things at a time. In this case, not the number of groups that you want to create, but the type of method, meaning the linkage function that you want to test. In this example, we're testing the average, single, and complete linkage function for hierarchical clustering and repeating the process of creating 3 different figures and then putting them together using the patchwork package. This way, you can quickly compare the results of hierarchical clustering when using different linkage functions.